Explorer.
Hello?
Yes?
So I'm on the line.
Okay, can we get the slides up?
And
you're going to have to give us a signal for next slide.
Okay, all right. Okay, this is a proposal currently in review for the Simplex program. So what we're proposing to do with the 6U CubeSat is to search for exospheric water in H2O and hydroxyl and oxygen molecules and the exosphere of the moon in ionized form. And furthermore, we will be able to determine the nature of the sources from the various time factors and spatial factors of the measurements, and from the fact that we can actually track the ions back toward their sources, either in the exosphere or on the surface. We have a collaboration here of Goddard, Maryland, and George Washington University, UCLA, and the University of New Hampshire. The latter two would particularly be involved if there were some collaborative observations with the Artemis spacecraft, and if LRO kept going, even with that one, although it may not. The big question we're asking here is exactly the question Abraham Lincoln asked many years ago, coming back from Washington through Niagara Falls, looking at the falls and not being kind of immune to the grandeur of the scene, as one of his comrades described it. But he was asking, where in the world did all that water come from? You know, and how did it get there? Where is it going? So we know we know that there, in terms of hydrogen at least, that there's 150 metric tons of water that could be locked up in the permanently shadowed regions of the moon. So that's, let's say, kind of an upper limit to what we see. Of course, various measurements have been telling us about surface water and OH and other things, including the L-cross impact. And if you assume that that water has somehow gotten there over 4 billion years from someplace else on the moon, the flow would be something like 40 kilograms per year, not per second, 40 kilograms per year, which just doesn't sound like a whole lot. But to measure that component in the exosphere, one needs a fairly sensitive instrument, and which is what we're proposing to fly, which will be an ion mass spectrometer. Next slide, please. I think I'll skip past this. The moon is not as dry as we thought from the Apollo days. There's water there clearly in various forms. We're trying to understand where it comes from and how it moves around. Next slide. Our three main objectives. So number one is to definitively detect and resolve the global abundances of water group pickup and related ions, which is to say ions that are produced by photo or other ionization of the neutral atmosphere of the moon and coming from whatever source. So the instrument we're proposing would be able to clearly separate molecular ions, not just atomic ions, but molecular ions. So O plus and OH plus and H2O plus, and also ions at lower mass like H2 plus and helium plus. If there was any H3O plus that you might expect for an enceladus type outgassing event, maybe an impact event, we would see that clearly. The second objective is to through basically a 6 lunation mission, 6 months, going in and out of the magnetosphere of the Earth into the solar wind, and observing at all local times, and we would be in a polar orbit, to sort of separate, as best we can, the sources, the probable sources that I'll describe in a moment. Objective 3 would be to actually follow the ion trajectories back to their source sites to try to correlate to the geophysical characteristics of those sites And for example, the polar craters. We will be doing that with an instrument that actually has 240 angular sectors, and it can be operated in different modes. The spacecraft itself can be turned. So it's a fan-shaped beam aperture, but the spacecraft can be operated to twist it around in different directions. And so if we do repeated observations over one site, we could potentially get down to 50 kilometers squared area resolution. Next, please. Where the sources, the ones that people are talking about that we want to look at are photo-stimulated desorption, UV irradiation, mainly on the lunar day side, which in that case there would be no correlations to other things like dust streams. The second is meteoritic impact vaporization that we're seeing clearly from the LOTI data is a factor in producing volatiles seen by LOTI. The third would be solar wind sputtering by surface bombardment. There can also be the surface processes of surface radiolytic chemistry, which may be turning oxygen and hydrogen from the solar wind and the surface into water. And lastly, we want to look at the potential effects of energetic particle radiation from cosmic rays and solar energetic particle events, which do tend to vary in time, and which affect the radiolytic chemistry of the near-surface environment, particularly if there was ice near the surface in the polar craters. It also affects charging, which can be a factor in the chemistry and the outgassing of any such gas. Next, please. The big experiment is simply to go to the moon and ride around in orbit in a polar 150 to 250 kilometer orbit around the moon, and do that for at least 6 months. And so what happens is you see here that the moon is, the yellow is entering into and exiting from the magnetosphere of the Earth and going in and out of the solar wind. The models are suggesting to us that we will see different time profiles as we enter and exit the solar wind, depending on what kind of process we're looking at. We would also expect to be, there would be impact events which actually are being monitored continuously from Earth. You see in the lower right-hand side about 3 impacts per hour. Those could produce impact events that we could see from orbit. Next, please. This is sort of a prototype version of the instrument that we're not going to talk about in great detail, obviously, but it is a wide field of view ion mass spectrometer, and so it uses on the right-hand side the aperture is at the top, and so that has a steering lens which guides ions through a sort of an electronic gate system into an electrostatic analyzer, which determines the energy overcharge of the ions, and then they pass into a time of flight system, which you see in the middle there with the thick green track. So it's being deflected by electric field, and which we can use. We measure the time of flight in that system, and that gives us the mass overcharge spectrum. The resolution of this thing is at least MOVDM of 30, meaning we can go up through sulfur or so with no problem. If we have large peaks, we can get even much higher resolution. Because we're doing the time of flight system with the gate, we actually get very high energy resolution, and we can resolve angles down to 2 degrees with the elevation angle system. Next, please. So these are some laboratory runs of a similar detector showing clear separation, in this case of nitrogen, oxygen, and H2O plus ions. Down below, what you see is sort of a blow-up of what was published by Tanaka et al. From the Kaguya ion mass analyzer. And so clearly, we are talking about a much improved mass resolution from what has been previously available for hot ions. We did not measure cold ions, but we also do not have the problem of background outgassing, because the ions we measured cannot have been created at the spacecraft at the energies that we're measuring them of hundreds to a few thousand volts. Next, please. So we are building at Goddard on Heritage from the ExoCube satellite, upper left, which is now taking data from a somewhat similar but a little bit less capable instrument on the Earth's ionosphere. Dellinger, the upper right, is approved once it finds a ride to go up to ISS January in 2016. And that one is a very close model to what we are flying. We would be flying for Hydrox, which is in the lower right. So there you see that we're using a solar electric propulsion system and with solar power, about 70 watts of available power. It takes about 50 watts or less to drive the SEP system. Launching in mid-July, takes about 14 months to get to our science orbit, and we want to stay there for at least 6 months and go beyond that as much as we could. The fans you see are just showing where the fields of view are for the instrument, which is quite wide. It's 200 degrees by 60 degrees. Next slide, please. Propulsion system has heritage from our partners at George Washington University. I will not go into detail on this. Next, please. Next slide. Okay, this is showing the trajectory. The main point here is about half the time on the way to the moon we are doing active low thrust propulsion, and so most of the power is taken up by the SEP system. At other times when we're not thrusting, we can be doing science measurements during cruise. Next, please. Next slide. Here you show the profiles for insertion into the polar science orbit, which takes quite a while. And of course, while we're thrusting down to that orbit, we can't really be taking much of any measurements. But once we get there, we're in a pretty stable orbit, and we'll make continuous measurements. We could actually extend this by choosing the right kind of orbits when we get there, and there will be very good prospects for collaborative operations, particularly with Artemis in orbit now. Next slide, please. Key points. So we have a absolutely fantastic near-term opportunity here to put a lot of CubeSats up in space, and some of them at the moon. So this has really fired us up to pull this proposal together. What we're concerned with is that there's all this water potentially deposited, at least observable as hydrogen in the polar shadow regions, which is coming from someplace, and we would like to be able to see that actively moving through the exospheric environment with this mission. We will not have problems with outgassing, because the ions that are produced near the spacecraft and accelerated in the spacecraft potential are far too low in energy to affect our measurements. We would like to go for a full 6 months or more. And we have a lot of capability in the spacecraft in terms of the 240 angular sectors of the instrument, the fully rotatable 3-axis control, and also the solar panels can also be rotated. And we think this would be a very excellent opportunity for science enhancement type work with Artemis and whatever else is up there, including the other CubeSats that would be delivered to the moon. Thank you very much.
Thanks, John. Is there a super quick question? All right, John, I think you're asking. Thanks for tying in.
Let me say that you can chase Menelaus Sarantos down the hallway asking questions. So he's on our team.
Super, thank you.